2. And the first question says to talk about the sample space, the sum of 2 die. What I tend to do when I talk about the sum of 2 die is I look at all of the outcomes of one die, and then all of the outcomes of another die over here. And I'm going to write their sum in the middle. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and so forth and so on. So that's just the sum. Then we'll go on this way, 2 and 1. You can kind of see a pattern here. Do you agree? I'm just going to fill in, just going to populate the rest of the chart really quickly. Make sure I'm doing this right. I skipped one. Sorry, I saw that. Thank you. Okay. Just kind of filling out that's really all the possible outcomes. If you wanted to write all the possible combinations. Now, I know they're not equally likely because if you look at, there's just a 1 out of 36 chance you're going to get snake eyes. Snake eyes, being a 1 and a 1. It's just kind of like, tails to me. Okay? There's also a 1 out of 36 you get a 12 in the sum of 2 die. Okay? But if you look at, what's the most common sum to roll? 7. Okay? So you can see that probability is 1, 2, 3, 4, 5, 6 out of 36. So 1/6 of the time, you'll be rolling a sum of 7. Okay? So that's just one way to organize and show the information for part A. For part B, it talks about a family has 3 children. Record the genders in order of birth. Well, we're looking at 3 children here. You can have a boy, boy, boy. You can have a boy, boy, girl. The girl can be in the middle. The girl can be in the front. All right, now we have 2 girls. Those 2 girls can be in the front. We can have boy in the middle, or we can have the 2 girls. Or we have all girls. Okay, let's see where Mrs. Magic lies on this one. Since I have 3 kids, I am here. Okay, not that it matters, but those are all the possible outcomes, right? Are they equally likely? Yes. They are. Because having a boy and a girl is equally likely. Now, I just say that. I don't know if that's necessarily true. If I want to be like a doctor about it, I'm sure that, because we won't get into that. But anywho, you get the idea. Supposedly, a boy and a girl are equally likely chances. And Nathan, which one? You said C was the hard one? Or was it B? It was B. Does that make sense what I did there?
Yeah, I was confused with 1B.
Oh, 1B. I'm sorry. Oh, a family has 3 children. Record the number of boys. So how is that different than just recording all the possible sample spaces? The recording of the number of boys is you can have no boys, 1 boy, 2 boys, or 3 boys. And that would be the outcomes. So it's just 0, 1, 2, 3. Okay? Again, not equally likely. Yes,
I didn't know how to write out the outcome for 2D.
2D. All right, let's look at that one. 2D says toss a coin 10 times and record the longest run of heads. Okay, so how many times are we tossing it? 10 times. Okay, so record the longest run of heads. So we're going to toss 10 times. And I'm looking for a number of heads. Now, not equally likely, okay? But we can have no heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads. So it's 0 to 10. That's the sample space. That's all you put. Okay, C? Okay, let's go back to C. Now, it's important to know that those outcomes are not equally likely. Right? You know that getting 10 heads in a row is probably extremely rare, right? But maybe getting 1 or 2 might be pretty common. So the further out you go, the question was, are the outcomes equally likely? I think was part of the question. All right, let's go to C first, okay? So 2C, do you have a question, Erica, about this one?
Yeah, I
All right. Okay, if you toss a coin 10 times, out of those, that run of 10, you're just supposed to look at the outcome of the number of heads. It said record the number of heads.
Okay.
So all you had to do was, in that toss of 10, what could happen? I could have all tails, which means I'd have 0 heads. I could have 9 tails and 1 head. So that's what the 0 through 10 is coming from. That's the number of heads. That's just one of the possibilities. Okay, that's all it means. A sample space is just a list of all the possibilities, right? That's all it is. All right, back to 2C. 2C says toss 4 coins, record the number of tails. Well, it's kind of the same thing, right? So it's just going to be 0, 1, 2, 3, and 4.
Oh my gosh. I didn't feel
Sure. And they're not all equally likely, right? Is that okay?
Yeah. It always confuses me.
Kind of like with this boy girl thing, rather than list them all out, it just if it said, for example, record the number of girls. Okay. This is kind of the way I did my sample space. I said there are 0 girls. This is 1 girl. This is 2 girls, and this is 3 girls. Not all equally likely, right? That's what that means. So 0, 1, 2, 3 would be the sample space if it said record the number of girls. Okay? If it says just the order of children, then I want the PPG thing. Okay. I think that's what I want on your quiz, right? It lists all possible outcomes. Yeah, I'm not going to make you list all possible outcomes for 10 tosses, because that would be phenomenal, right? And that would take up 2 pages of paper. All right, let's go ahead and go on to question 4. Let me read the answers, and then we can go over whichever you want, okay? So I'll just pause this since you don't want to listen to this part. So let's start with 6, and then we'll go on to 8. All right. So question 6 says, employment data at a large company reveal that 72% of the workers are married. So I'm just going to write this down because I think you have to do something with the numbers. And then it says 44% are college graduates. Hopefully you realize right away that those don't add up to 100%, which tells me what? That there's probably an overlap somewhere. You can be both college and married. Would you agree? Okay, that's what that should tell you. All right, and it says half of the college grads are married. Right? So half of the college grads are married. Okay. And then it says, what's the probability that a random worker is? So I think what we should do is we should probably draw a Venn diagram. Wouldn't you say? If we know that they can be both college and married, then we know that the Venn diagram should look something like this. Would you agree? All right, so let's just fill it in. So I have college here, and I have married here. All right. So it says that half of the college grads are married. So let's start with that information, because that's kind of like the both part, right? So college grads is 44%. What's half of that? So 22% is your both. I'm going to put 0.22 in the middle. Okay? Which tells me what percentage is college only. 22% off. So we're going to put that on the outside. Okay? Now we'll look at married, and we have 72% total is married. So since I already have 0.22 in there, 0.5 or 50%. Okay? Now if I add all those up, we're still not at 100. So what percent has neither been married nor gone to college? 6%. Okay? So that's your Venn diagram. So let's now use it to answer the questions. Part A says, find a probability that a randomly chosen worker is neither married nor a college graduate. Which number on the Venn diagram is that? 0.06. Got it. Okay? We can also do it with, well, there's a formula way to do it too, but let's pick one way. Is married but not a college graduate. What's the percent? 0.5. Is married but not Just double checking, good. And then part C, is married or a college graduate. Is married or a college graduate is adding all of those up in the Venn diagram, or 0.94%. I'm sorry, 0.94 or 94.
Okay, where did you get the delta? Because I see I have the 0.22 in the middle there, but you have to subtract the 72 though, or is that not true?
Yeah, we had to subtract 0.22 from 72 to get to 0.5. Because when we're looking at the married, everything in the married circle has to add up to 72%. Is that better? Anything else?
76.
Better? All right. You can also do this last one if you want, and I'd like to show you with the formula. So in case we're stuck, if we want the probability of college or married, let's do probability of married or college. There we go. Let's go ahead. So probability of married plus the probability of college plus the, I'm sorry, plus, what do I have to do in my formula? Minus the probability of married and college. Isn't that just the formula, the addition formula for or? Just put it in context. Anytime, Jordan, that you do this, you're going to show me work, right? So this is an example of some work that you could do, right? Show me what you type into your calculator, right? I really, on a test or quiz, need to see either a Venn diagram for this problem or I need to see the context equation. I use M's and C's rather than A's and B's. That's really the only difference, right? So I'm going to plug in what I know. The probability of married is 72%, or 0.72. The probability of college is 0.44. Minus the probability of married and college is 0.22. When I do that, I do get the same thing as adding everything inside the Venn diagram, and I get 0.94. Yes, Charles?
Couldn't you just use 0.22 and 0.5 and that would split it since they're already split?
If it doesn't have
Oh, it's the second split.
right. Everyone, so yes. You answered your own question. Okay, yes.
So I get confused with like how it's set up with the letters. Like
Okay, Jacob, you have your formula sheet. So I want you to look at your formula sheet. We're going to need it anyway today, so you might as well get it out. Okay? Look at the first formula on the formula sheet. Do you see how it has A's and B's in there? All I did was replace A with M and B with C. M and C is married and college. Sorry.
so I get confused with the U and the and or.
All right, so that's the part. So this is and. Helps me remember because I can make a little bar across it with an A. And then this is or. And it looks like A if I made it a full bar.
But what would you do with the like in the middle?
Oh, for the and, we're going to get to that today. We haven't really talked a whole lot about that yet.
Do you know what the or is?
The or does this. One or the other. After we've done that, that's the big diagram.
So or is that.
This is the or problem.
And it's plus and minus.
Yes. Yes.
So you don't take that last part. You don't actually multiply them.
Sometimes you have to, because the and, what and means one and the other, right? But because these are not necessarily independent events, and we're going to talk about that today, if I multiply 0.72 times 0.44, I don't get 0.22. They're not independent. So you can't multiply them unless you know for a fact they're independent. We're going to talk about that today. But since we were given the information of, because it says half the college grads are married, right? We're given that number. Often we are. But sometimes you're right. Sometimes we're not, and we have to multiply them. And we'll talk about that too. Okay? You feel a little bit better about the homework? I hope. Okay. Can we go back to the warm-up now? Because I think the warm-up is getting people some grief as well. Hopefully you drew a question. same thing as what we just did. So what I'm doing now is up here.
118 is
You guys, actually, Brian has a pretty good question. 8D. You want to look at that one real quick? Okay, let's do that one. I didn't realize that it was given to you in a different kind of way. Do you mind if I look at that one before you do this? Okay. So, let me do that one. All right. So let me just really quickly draw the problem here. So we have birth order, only because it's important to look at the chart. And this will help a little bit with what we're doing today also, which is a good thing. And then we have how many rows? First four only. And then we have second or later. I'm just recreating the chart on page 360. All right, over here we have arts and sciences. And then we have agriculture. Then we have human ecology. And then we have other. All right, and then we have the book. Let me put the numbers in here. We have 54, 52, 15, 12. Oh yeah, 130. Sorry about this, guys. I agree that it's a good question, but it's written differently. In all of the other problems, aren't we given percentages? This is the first one where we have to use a two-way table to come up with the probabilities. So I agree with Brian, it's a little bit different. Okay? So let's go through, I don't mind doing all the problems. Do A, B, and C, and D. Fine with me. Okay? So if we look at A, it says, what's the probability that we select a human ecology student? So back when we did contingency tables, back in the second unit when we did categorical data, we looked at these and we came up with probabilities. Do you remember that from a while ago? It's kind of like a review of that in a way. All right? We're going to kind of put that together with the addition formula or the OR formula. So, to read it again. What is the probability we select a human ecology student? So the probability of human ecology is just going to be the total of human ecologies divided by the total. If you agree with that. Yes, no, maybe so.
Yeah.
Okay? So that's A. And then you can divide that on your own time. I don't care. It's actually more valuable to me if you leave it this way because I can see what numbers you're using. Would you agree? To me it is anyway. Both is fine. Yeah, I would prefer both actually. But yeah, that's fine. All right. Part B says, what is the probability that we select a firstborn student? So firstborn, or only student, is 113 divided by, so the probability of firstborn is just going to be the total of your firstborns divided by your total. Would you agree with that? Okay. I'm getting messy, so I'm going to go ahead and go to C. C said, what is the probability that the person is firstborn and a human ecology student? Probability of firstborn and human ecology student. Well, using a contingency table, we can find that out pretty quickly because we're just going to look human ecology and firstborn. Well, there's 15 of those. Would you agree? So it's just going to be 15 divided by 2.3. Remember this from before? I hope. Okay. All right, let me change colors here. We have D. Now this is the harder one. Okay. D says, what is the probability that the person is firstborn or a human ecology student? So let's look at that. I'm going to write it out first. What's the probability that they're firstborn or a human ecology student? With me so far. I'm just going to use the addition formula, or the OR formula that we just looked at. Okay, in the first formula on your probability column. I'm going to write it in context here. If it's an OR, we know it's the probability of first plus the probability of human ecology minus the probability of first and human ecology. In context, are we okay with that? Just using the formulas, all I'm doing. Sure? Steph, no? I don't feel that second for later at all. Not even brought up. Not even able to pay attention to this. I'm just worried about the question said, what's the probability of first or human ecology? So I'm only dealing with those two things. Okay? All right, so I'm going to plug in what I know. Believe it or not, we found all of it already, didn't we? So the probability of first is 113 out of 223. Plus, the probability of human ecology was 43 out of 223. Minus the probability of first and is 15 out of 223. Look at all that work, Jordan, that you need to do to answer this question. Wow. I did it on my calculator. So did I. So how do I answer the question? What's 113 plus 43 minus 50? Because they all have a common denominator. Can I just add the numerators and subtract the numerators? So 113 plus 43, 156 minus 15, 141. Right? Does that answer the question, Ryan? Thank you for bringing it up. I didn't realize it was that big a deal. I appreciate it. You see it differently? All right. We're going to come back to the idea, hopefully today, of a contingency table, because we can actually do what's called conditional probabilities with them as well. So we'll come back to this idea in a few minutes. We might actually use this very one as our example. We'll have to see. But can we do the warm-up now? Let's make sure we know. Hi, Hunter. You're going to sit there. You have to stay away. That's part of the rules. You're not so, tempted. Yes, we did. All right. We need to draw a Venn diagram with this situation. Why? What is the key word that tells me Venn diagram? Both. I see the word both, so I know I'm going to do a Venn diagram. So let's make sure you have your Venn diagram drawn properly. So we're going to have a breath test, or we're going to have a blood test. Let's fill in the numbers. Where should we start with the numbers? Hunter. In the middle, in the both parts. So 22% goes in the middle. That's a coincidence. That's the same as the last one, by the way. Not always 22%. And then we'll just kind of work backwards. 36 is a blood test. So what would this be? 1.4. And then 78 are breath. So 0.56. And if I add them together, do I get 100%? So what is the other one? 0.08, 8%, right? All right. There's our Venn diagram. Let's use it. What's the probability that they took a test, period? 92%. You're adding all the middle, right? One or the other. A breath. Another way to say that is a breath or a blood test. Okay? And that would be 0.92. With the Venn diagram, it's easy to see. A blood test or a breath test, but not both. That's simply going to be 0.56 plus 0.14. See how it's different? Yeah. Okay? So this is 0.56 plus 0.14, which is 0.7. Neither test, 8%. Amanda, is that clear what the difference between A and B was? Okay, excellent. Good. I think that's catch up now. We've done everything we can to everywhere. Feeling better about Venn diagrams and probabilities and things. Condition rule is okay. Because now here's the new stuff. Okay? So. Yes, please. It's note time. If you want to print the notes off at home, I'm fine with that. I just want you to be awake and paying attention. Okay? All right. So I kind of alluded that we were going to be doing this where we talked about a contingency table, and we're going to look at something called a conditional probability. Okay? So this is a different contingency table. It's talking about whether you're a boy or a girl, and whether your goal is to get good grades, to be popular, or to play sports. Okay? We did a little survey, and this is our results. You probably need to fill in the totals. Would you agree? So take a second and copy this chart down, and let's answer some of these questions here. Double check my arithmetic, please. Definitely not my forte. Oh, I'm right in my standing. I gotta stop. Alright, so copy it down. So, this is kind of like what we did for homework, at least the first couple of questions, but we have to be careful about the way that it's worded. And we did this type of stuff before, I just didn't call it conditional probabilities, okay? Probability of selecting a girl. So what would the numbers be? Let's leave them as numbers, not change. Let's leave them as a fraction. Let's not change them to decimals so we can see where they're coming from. There. Divided by? Perfect. Okay, exactly. Probability of selecting a student with the goal to be popular. Who wants to do that one? Aditya, help me out. Aditya, you like got all, your voice got all higher than you ventriloquism and like threw it across the room. That's pretty impressive. Go ahead, Aditya. What's number 2? Goal to be popular. What's the total of popular? Oh, all right. And then we're going to divide it by the total, okay? All right, here we go. Third question. What's the probability of selecting a student who is a girl and wants to be popular? And means and wants to be popular. Isn't that 91 divided by 478? Okay. I agree with you. Now, I'm going to stop there for a minute because I'm going to ask a question. Because Stephanie asked me earlier, doesn't and mean that you just multiply them together? Do you agree with that? And up to this point, I have said yes, right? Let's just double check that theory, because I think that's a good thing to look at. So we want to go ahead and look at what's the probability of girl and popular. Okay? So girl is 251 out of 478. Popular is 141 out of 478. Are those two things the same? Let's test it. Go ahead and type them into your calculator. Tell me what they are. What are those? We'll give them as decimals to compare here. And let's figure out what they are. So I got 19% on the right-hand side. This is 0.19. Is that the same as the left-hand side? Let's see. .155. something very important. That tells me that these two things are dependent on each other. We just mathematically proved it. And I'm going to say that again because it's really important. If you multiply two things together, okay, two probabilities together, and they do not equal the and, then we know that being a girl and being popular, or a goal of being popular, are not independent. They are dependent probabilities. Okay. Dependent. Okay. And we're going to look at what that means in a minute. Okay. Oh, I just answered. What's wrong with using our multiplication rule for this question? Because they're dependent, you can't. Okay? So we just kind of said, answer it. Fair enough? Okay. So, let's talk about the multiplication rule for dependent events. If events are independent, we could just say that the probability of A and B is A times B. Would you agree with that? At least that's what we've set up to this point. But if we have dependent probabilities, or dependent events, this is the new formula. And I apologize for the crazy font, okay, but you need to write this down. Okay? Keep your formula sheet handy, because I'm going to show you where it is on your formula sheet as well. Actually, it might be written this way. Let me see what it is. No, it's not really exactly this way. Well, write this one down for me. The probability for if A and B are dependent, then it would be the probability of A times the probability of B given A. Okay, a little bit different. That little line between the B and the A is red given that. Okay? So this is red. What the probability of A and B equals probability of A times the probability of B given A. Okay? So, if you look at your formula sheet for me, and you look at the second formula, you'll see it looks similar to this. Would you agree? Look at yours. Find your formula. What should you be looking at? What is the difference between that formula and this one? I divide, the one on the formula sheet has this by itself, doesn't it? But it's divided by that. Or in other words, oh, hang on, that's something different. In other words, it's this. I apologize for crazy. I don't even know what to say. It's fine. That's what's on your formula sheet. You know, that's what's there. Right? I know I have stolen somebody's thing. I know. The probability of B given A is just equal to the probability of A and B divided by the probability of A. Okay? It helps me remember when I'm looking at these that the given that and what you divide by are the same. Given that. That's how it's written. It's what we call a conditional probability. Okay? And we're going to look at some examples of that in just a second. But notice what given that and what you divide by are the same. Okay? We're going to put this in our own context as well. So let's rewrite it in a different situation. Let's say, how would I write in context the probability of A given B? I think that's the one that's on your formula sheet, right? Yeah. So A given B is the probability of A and B divided by the probability of B. That's what's given that. What would the probability of hat given tomato be? The probability of those because it's the same formula. You're just putting it in context, that's all. Okay? So let's look at a situation. Let's go back to our boy-girl totals here. All right, and I gotta put my totals back. Oh Lord, help me out. All right, so we have 247.
141.
Thank you. 90.
478.
Thank you.
51 and 227.
No, that is
The other way around.
Okay, sorry. So let's look at some more calculations with this, okay? And using our probability rules when possible. Let's see. What is a probability that a selected student is a boy and has sports as a goal? So what's a key word? And. I really want you to think about keywords here, okay? We know the word both means Venn diagram. We know the word and means multiply. What we're multiplying maybe works. When we have a contingency table, we can use the contingency table a little easier. So, probability that boy, we have a, here we go. Boy and sports is a goal. So what would that be? 60 divided by 478. I agree. Okay? Probability that a student is a boy. What's the key word in this one? For number 2. Or. Okay? This kind of looks a little bit like the homework problem that we did, number 8, doesn't it? Okay. Huh? Boy or, yeah. All right. So, probability, so I want you to do this one since we did one just like it. Okay, this is just like 8C on the homework, right? Or 8D, I'm not sure, the last one. So you try it. I'm going to pause the recording, write the formula out in context, and plug in the numbers. Hopefully this is the context you put, and we'll fill in the probabilities in a minute. Boy or sports is the probability of boy plus the probability of sports minus the probability of boy and sports. Do you agree? That's what I'm looking for when I say write the formula in context. That's what I mean. Okay? That's it. That's what I mean by formula in context. Well, I'm not done. I gotta put numbers in now, right? Okay? Now put the numbers in. Probability of boy was 227 out of 478. Probability of sports as a goal was 90 out of 478. Minus the probability of boy and sports is 60 out of 478. And then we could go ahead and answer those questions. So we have 227 plus 90 minus 60, so 257 over 478. Okay? Now, let's look at number 3. Because number 3 is a little bit different. Look at the wording of number 3's question. The probability that a selected student has sports as a goal, given that they are a boy. Okay? So, let's write this in context first. And we're actually going to do it 2 ways. First way, we're going to use the formula. Okay? The probability that they have sports as a goal, given that they were a boy. So that's what I'm looking for. Okay? How can I rearrange my equation that you see here, or you can just look at this one, you don't rearrange, just putting the S and the B into the A and the B, right? So we're going to go ahead and plug it in. So in context, this is the probability of sports and a boy, which by the way is the same thing as boy and sports. The order does not matter there. Divided by the probability of boy. Are we okay so far? Now I'm plugging in numbers. The probability of sports and a boy. We We found that at the beginning, didn't we? Wasn't that 60 over 478? Divided by the probability of just boy was 227 over 478, which ends up being just 60 over 227, which is approximately 0.264. The 3 decimal place is a good rule of thumb, okay? You understand where the numbers came from? Good. We can also do this if you look here. So we're okay with the formula, right? Yes. Which is great. The formula always works. But if you're given a contingency table, there's a shortcut. Let's look at these two numbers. We're looking at sports given that you were a boy. So we're looking at 60 and 227. Look where they are in our chart. 60 out of 227. The probability that they would like sports given that they were a boy. Look at what numbers came from that. So if you're given a contingency table, you don't need to use the formula, do you? You can just go ahead and you know the given that is the total that you divide by. Okay? Because this is the and, isn't it? And then you divide by what you're given now. So that's a shortcut. But you're not always given a contingency table, right? But if you are, use it to your advantage. How are we doing so far? You have a question?
When it's 50 over 478.
If they're both over 478, can you reduce the fraction to just be 60 over 227?
I was thinking
We never cross multiply because nobody wants to do that. This is what's called a complex fraction. Okay, so the next question, the last question we have for today is, and this is something you will see in your homework as well, is gender, and this is your gender, right? Is gender independent of your goal? Okay, we already know the answer is no, because I showed you a minute ago that they were dependent. But how could I prove it? So, a couple of different things. So I'm going to say it again. Is that the next slide by chance? It's not, of course. So, is gender independent of goal? In other words, are the two things in my contingency table, whatever two variables are they independent of each other? And there's two things we can do. Okay, we can look at what we call the conditional distribution versus the marginal distribution. Remember how we did that before? We did that back in I think back in September. Okay? But we're going to use the formulas to show. Okay? So, you don't have to do them all, but you can pick one. Since we're dealing with sports and boys here, can we use that since we have a lot of the information already? If they're independent, you have to show this, that the probability of boys and sports is equal to the probability of boys times the probability of sports. If that is true, then they're independent. If it is not true, what is it? Dependent. Okay? That's something you can pick. You can pick any. You could have picked girls and popular like we had earlier. That would have been fine. You could have picked girls and what's the other one? Good grades, right? That would be the other one. So any of those combinations would be fine. So boys and sports. What is that probability? Boys and sports. Sports and boys. It's 60 out of 478, right? Hunter, are you writing this down?
Yeah, I'm like,
I hear your voice. Okay, good. Probability of boy again was what? 227 out of 478. And then the probability of sports was 90 out of 470. So, this is a question mark. We're not sure if this is true, right? So let's go ahead and do the division. So 60 divided by 478 is 0.1255. Is it the same as the other side? We'll go ahead and multiply these together as well. And I get 0.089. Are they the same? No. Now, how close is close enough? What if I had 0.123 on the other side? That's pretty close. Okay? These are definitely not close. So, I mean, you want to be close enough. I don't even know how to explain it. You know, I'm not going to give you a rule that has to be within 0.01 or, you know, a hundredth of. I'm not going to say that. You have to make that kind of educated guess on your own, really. Yes. Has to be close. Yeah. And I would say that, you know, a tenth off is close enough, but, you know, I'm not even sure a tenth. No, not the probability. 100, maybe to look at. If it's close, but it's not, you're not sure, try a different combination. Try girls and big grades. And try that one, see if that one works any better. Okay? But because they're not, what do we say? Are they independent or are they dependent? They're dependent. And this is the mathematics that's needed to show that. Okay? So, when I ask the question, I'm going to say this again, Erica, so please make sure you're awake. Okay. Okay? If I ask the question, are they independent? You're going to have to write the formula in context. So I know what numbers you're using and where you got them from. You're going to have to show me the numbers in it, and then calculate whether they're the same and make a decision, independent or dependent. So all of that is needed for a complete answer. Okay? Yes, no, maybe so?
Yes.
All right. How did today go? All right? Good. All right. We're done with new stuff. Let me give you your homework. Let me give you your homework. You have homework. It is 8:55. So, chapter 15. Good. Okay? Got it. All right. So we're going to say, I want you to do problems. Now, number 9 deals with the cards and the deck. So remember how we talked about that before? There's 52 cards, and we know about a suit. So make sure that you realize that. I think we're going to do like 9 through a whole bunch of them. Yeah. 9 through, it's an AP class. I have work to do too. Oh my God. 9 through 14.
You better go home.
And I'm going to give you one other one, folks. And I'm going to give you number 30. And that's it. Number 30 is the question, is it independent? Okay? That's it. That's it.